Hi, in this video, we want to take a look at multivariate normal distribution, and then we want to look at moment generating functions, specifically the moment generating function for multivariate normal. Okay, so how we're going to construct multivariate normal is we're going to take standard normal for a vector of standard normal distributions, then we're going to transform the distribution of that vector into a non-standard normal multivariate distribution. Okay, so let's first start out. We're going to go with independent standard normal IID random variables. So let's go ahead and say that we've got a bunch of z's, and they're going to be independent standard normal. So that is to say that mu is always equal to 0, sigma is always equal to 1, or sigma squared, however you want to look at it, for all I. And we're going to go ahead and say that covariance is equal to 0 whenever I does not equal j. All right, so this part right here tells us that our covariance matrix is the identity matrix. That's going to be important. Now, what we've also got, since I'm saying that mu is always equal to 0 for each of the individual z's, that means that the expected value for the vector of z's is going to be the 0 vector. Shocking, I know. Okay, so let's go ahead and let's start from here. And let's go ahead and get the density for the vector of z's. All right, well, first I'm going to take the density of the entire vector. And so, you know, it's g of z1, z2, z3, all the way through. And of course, that's just going to be the density of vector z. And here, if you really get nitpicky, you'll notice that I am overusing, I'm recycling the letter g in this, but I think it's clear. If it's not, shoot me an email. Okay, so we have independence. Once I have independence between variables, I know that I can factor the density. Now, we're in the situation that any combination, any way we can look at it, we're going to have independence. There are more exotic situations where we have like 3 variables and 2 are pairwise independent, but the 3 of them are not. We're not going to be dealing with that. We're making it so that everything just factors out nicely the way we want it. So here, this density will factor into the individual densities multiplied together. So this converting to this just comes from independence. Now, here I'm saying G1 because this will be the density of the first variable. G2 because it's the density of the second variable, all the way down to G sub P, which is the density of the pth variable. Okay, all right. I mean, we know about that from stat theory. Now, I'm going to use the fact that all of these have the same density. Since they all have the same density, I get rid of the subscripts. I just say it's G. Just say that it's, you know, G for each individual one. And now I'm going to invoke that I know that the density is a standard normal density. And so then I'm going to replace this with standard normal, replace this with standard normal, keep on going down the line until I get to the very end, which I replace with standard normal. Okay, now let's take a look at this. I've got this algebraic expression. I've got a bunch of 1 over square root of 2 pi, p times. So, and I'm multiplying. I'm multiplying the same thing by itself, p times. So I know that I can just put that to the power of p. Boom, we've got this. Now, I'm multiplying a bunch of e's together. Well, remember, e, multiplication, converts the exponent into addition. And so here, I can see that I've got in the exponent, negative variable squared divided by 2, negative variable squared divided by 2. And they're in exponents. When I multiply these together, I know it's just going to be a summation. Now, this sigma is the summation sigma, not the sigma for covariance that we'll be dealing with later. Okay, well, I know that if I take the sum of the squared entries, that is the same as the 2 norm squared. So I can replace the sum by the 2 norm squared. And so now I have the density for G. So here, if I know the distance of a vector from, or the tip of the vector from the origin, and I'm in standard normal, this density tells me what is the value of the density itself. Okay, okay. Looking good. So that's standard normal. You know, this should feel rather natural. All right, so what we're going to do, we're going to go ahead and say that vector z is distributed normal. Now the mean is the 0 vector, and the covariance matrix is the identity matrix. All right, I mean, that seems natural to this point. This doesn't seem like it's that far off from what we've done with univariate variables. Okay, so now let's do multivariate normal. Now, what we're going to do on this one, let's say that I'm going to make a new variable. I'm going to take some covariance matrix I'm interested in. I like this covariance matrix, and I'm going to go ahead and take the square root. Remember, when I have a positive definite matrix that's symmetric, there's always a square root. So every covariance matrix has a square root. Now over here, let's say that I'm interested in a particular mean for my vector. What we're going to do, we're going to take my standard normal. I'm going to multiply by the square root of the covariance matrix that I want, and then I'm going to add on the mean that I want, and that's going to be my new vector y. Okay, so what I'm doing is I'm doing a transform on the standard normal distribution. All right, so now let's think about it for a moment. Back in the day when I was doing, introductory statistics, if I had like sigma times z plus mu, that gave me a standard normal with sigma squared as the variance and mu as the mean. Well, I'm doing something very similar, but now I'm doing the vector version of it. I need to have a matrix here for the multiplication, and I need to have a vector here to get the expected value where I want it. So remember that sigma is a covariance matrix. It's positive definite and it's symmetric. Mu is a real vector, so it can take on any real values, and we're not going to be worrying about complex numbers or anything like that. We're keeping it real, yo. Okay, so, and something about this is that mu and sigma are constants. We're not worrying about hyperparameters, and we're not treating these as variables. That's for another class. We're not dealing with it because we want to get to linear models. Okay, so now let's think about this. If I choose this to be the transform that gives me y, first thing I'm going to ask is what's the expected value? Next thing I'm going to ask is what is the variance? And then third, I'm going to ask about the density. That's what we always do, right? That's what we did in stat methods, or excuse me, stat theory. That's what we do in mathematical statistics, and we're doing it here. So I'm going to take the expected value of y, which is, well, the expected value of how I defined y to be. Okay, well, expected values, remember that's integration, and addition of things inside an integral breaks apart. So boom, I get this. So the expected value of the sum is the sum of the expected values. Now, if you remember from chapter 2, way back when, that I'm multiplying by a constant matrix. I'm multiplying by a constant matrix means that here I can factor that matrix out. Boom, I've got that. Now, mu is a constant vector. Since it's a constant vector, the expected value is itself. Okay, so now we have our constant matrix times the expected value plus that mu. All right, well, what's the expected value of the z vector? Well, it was 0, right? Right. From our derivation, we know the expected value of each of the z's is 0. Therefore, the expected value of the z vector is the 0 vector. What's any matrix times a 0 vector? The 0 vector. And so 0 plus mu is, in fact, mu. Boom, we got it. Okay, so that gives us the expected value. Let's move on and take a look at covariance. Okay, so for the covariance of y, I'm going to take the covariance of the transform on z, very natural. Now, remember, like if I was doing variance on something that had a constant added on, adding a constant doesn't change my variance. That fact still rings true for us when we're dealing with vectors, that adding on this vector does not influence the covariance. Therefore, I know that this isn't a part of the story. I don't need to worry about it. Now, do you remember taking covariance of univariate variables? If I had a scalar times the variable, I ended up multiplying that scalar, I took the scalar squared times the variance. Remember that? All right, so if you remember from previous session, that what we end up doing is we end up multiplying on each side by that. Okay, so that's like the matrix version of the squaring by the scalar. Okay, so now I've got the covariance of Z. What's the covariance of Z? If we remember, it is the identity matrix. Boom, we put that right here. Okay, so now I just multiply these together. Well, the identity times anything is what I'm multiplying by. So this is sigma square root times sigma square root, which is in fact sigma by the definition of sigma square root. Okay, so we know that the covariance of Y is the covariance matrix that we were interested in the first place. Okay, so this gives us a way to go from a standard normal multivariate distribution to really any version of, we could use this transform to get any multivariate normal distribution that we wish, using like a random number generator or using like a density pencil paper work, something like that. Okay, so now we've got the expected value. We've got the variance. Now, next thing we always get, we get the density. Okay, so for the density of Y, we're going to need to use the Jacobian. Hopefully you remember the Jacobian from calculus or differential equations or something like that. All right, so let's think about what Y is in terms of matrix multiplication. Well, Y is equal to square root of sigma times Z plus mu. Okay, so if I need the Jacobian, I need to look at each individual variable of Y and take the derivative with respect to each individual variable of Z, right? Okay, so Y sub I, using the matrix multiplication formula, I know that's going to be the sum of square root of sigma ith jth entry times the jth entry of Z. Add these all up and then add mu sub I. All right, so the mu sub I part comes from here, and this sigma part, the summation sigma, different sigma, comes from matrix multiplication. Okay, so now let's go ahead and take a derivative. If I want to take the partial derivative of Y sub I with respect to Z sub K, well, the mu is disappearing because it's a constant. Okay, well, the only time I have a non-zero term in here is when Z sub K is in the formula. All right, so when I take the derivative with Z sub K, then all the derivatives for the Z's are going to be 0 except for that one Z sub K, and then I get 1. And I multiply by, what's getting multiplied by? Boom, we've got that the partial derivative of Y sub I with respect to Z sub K is in fact the ith kth entry of that matrix. All right, well, that tells us that the Jacobian is equal to the square root of sigma. Okay, so now we need to go back and do some matrix calculus, because now that we have the Jacobian, let's go ahead and get going. All right, so if I want the density of Y, what I'm going to do, I know it's going to be the density of Z, but with a transform going on. So we're going to have to transform back in a moment, times the absolute value of the determinant of the Jacobian. Now, something about this is, remember that sigma is positive definite. Since it's positive definite, all the eigenvalues are positive for sigma. Well, when I take the square root, using some stuff that we haven't really talked about, I know the eigenvalues are going to correspond to square roots of eigenvalues. Boom, it's going to be positive. So I don't need to really worry about absolute value bars anymore. Okay, so I know that I have g of the z vector times the determinant of the square root of sigma. and then I pull this out. See, there should be a negative, there should be an inverse on this. All right, well, let's keep on going there. Yeah, there should be a negative sign up here. All right, well, it made a mistake, but look at the book if I got it, if I'm confusing you. All right, so let's keep on going. Okay, so now I've got the g of z. Well, I don't want z, I want y, right? So I'm going to convert over, and I'm going to replace this z with this term right here. I'm going to go ahead and slap that in. When I do that, so first thing I'm going to do, I'm going to replace g with the e part, like this, just using the formula, and I'm going to divide by the square root of the determinant of sigma. Okay, and now all I do is I take this formula and I replace the z everywhere that I need to. Okay, so when I do that, remember, this is a norm, so it's going to be the vector transpose times the vector. Okay, so I take this, I take its transpose, I multiply it by itself. The transpose, remember, when I take the transpose, I switch the order. So the y minus mu comes out front, and the negative square or negative exponent 1/2 of sigma, that gets moved over here, and I'm hitting it with a transpose. Now, remember that sigma is a symmetric matrix, so the transpose doesn't do anything. So here, this is in fact sigma to the negative 1/2. Well, I've got sigma to the negative 1/2 times sigma to the negative 1/2. Multiply together, I get sigma to the negative 1. Boom, we got it. All right, so now I just started cleaning it up a little bit, and I can see that this is the multivariate normal density. All right, so we got it. All right, so how are we going to write this? How are we going to abbreviate this? Well, what we're going to do, we're going to say that the vector y is normally distributed with mean mu vector and sigma as the covariance matrix. So something that's nice about this is that if I have, let's say I generate some standard normal random variables using a random number generator, or pseudo-random, whatever you want to say, I can use, if I have a known covariance and a known expected value that I want, I can use this formula to convert to what I actually want it to be. And this can, this is a way to generate any multivariate normal distribution I actually want. Okay, so the determinant of the covariance matrix is called the generalized variance of the y vector. All right, so because of the negative exponent, f of y decreases as y minus mu at norm to norm as that increases outside a radius of mu. So actually, this should be increases outside radius of mu. All right, so what I'm trying to say here is that if we keep on moving out, we know that the density is going to decrease. Why do we know that? If I look up here, if we get far enough out with y minus mu, then when I multiply this out, it's going to get to be a larger value. And so a larger value times negative is going to be a larger negative. Exponent of a large negative is going to be super, super small. Okay, so we know that outside of a certain open circle in higher dimensional space, if we keep on moving farther out from the mean, the density is going to decrease down to 0. All right, so now another thing is that a small generalized variance indicates that y tends to be close to mu. Or another thing that could happen is that if I have small generalized variance, this also may indicate collinearity among the y's. So it could actually be both situations, because if two variables are very, very close to each other in terms of collinearity, then that can actually shrink down that determinant for us, even if everything else is pretty well spread out. And so that's like if we were to drop the, in that situation, if we were to drop the second one that is collinear, it's possible to get a larger generalized variance. All right, so now let's think about univariate normal. If I have y is equal to sigma times z plus mu, mu is a real number, sigma is greater than 0, this is going to correspond to y vector is equal to the square root of sigma times standard normal vector plus the mu vector. Okay, and so here we can see it's like, you know, this is the square root of the variance. This is the square root of the covariance matrix. Z is equal to y minus mu over sigma. So here on the bottom, I have the square root of the variance. Z is equal to the square root of the covariance to a negative exponent times y minus mu. So we can see that there's like a pattern here. We can see that this actually includes this over here as a corollary. And I can go through and I can look. I've got one variable. Here I've got p variables. I've got one, you know, standard deviation. Here I've got the square root of generalized variance. So square root of variance, the square root of the determinant of the covariance. And we've got exponents going on. So, you know, we can see that, you know, there's definitely a correspondence going. All right, now, what is it that the sigma squared and the negative exponent sigma do for these densities? Well, what these actually do, all right, this rescales the density to have a different variance. Over here, this transforms to covariance and rescales the variance of each of the variables. So in effect, it's transforming the density in terms of spread either way. Now, what does the 1 over sigma do? Well, the 1 over sigma rescales this density so that, I should have a square right there. I'm so ashamed of myself. The 1 over sigma rescales so that the density integrates to 1 so that we have a proper probability density. Well, what does the square root of the determinant of sigma do? Well, it also rescales the density so that it integrates to 1. All right, now let's look at moment generating functions. So if y is a continuous random variable, so we're not going to worry about discrete, we're going to keep things pretty simple on this one. For this discussion, all of the assumptions needed for the calculations to work are in effect. So we're not going to be dealing with things like the Cauchy distribution. We're not going to be dealing with anything too exotic. Just as we go through, the expected value exists. The integral is, you know, well defined. We're not going to have anything funny going on. All right, so y is a continuous random variable. Then the moment generating function for y with variable t is the expected value of e to the ty. Now notice that in this situation, t is considered a constant and y is an actual random variable. Now we need t to be defined on some open interval that includes 0. Now the textbook says like negative h, positive h, or something like that. It doesn't have to be symmetric. We can actually get a little bit more exotic, but 0 needs to be in there. All right, so if y is normal, mu and sigma squared, then this is my moment generating function. I have e to the power of mu times t plus sigma squared t squared divided by 2. Now, if you're going to take the actuary exam, you need to know that formula, by the way. Okay, so now let's think about moments. These are called moment generating functions. Why are they called moment generating functions? If I take the derivative and then I plug in 0, I'm going to get the expected value of a moment. All right, so from what I've said before is that a moment generating function is the expected value of e to the t times y. All right, so I know that the moment generating function is equal to the integral of e to the power of ty times the density. Okay, well, let's go ahead and take the density of both sides. All right, if I take the density of both sides, or sorry, the derivative. If I take the derivative of both sides, then I have the derivative of m with respect to t. Now notice t is the only actual variable in this situation. That's an important point. and I'm taking the derivative with respect to t of my entire integral. Okay, so I have a derivative outside an integral. Now, something should be kicking off in your head. Hopefully you took analysis. Hopefully you took advanced calculus. You know that you cannot go willy-nilly switching the order of limits. You know, limits do not function the way regular numbers do. Okay, if I can use something like Fatou's lemma, dominated convergence theorem, or monotone convergence theorem, I can go ahead and switch those limits. And so for this situation, we can do that because there's the dominated convergence theorem does apply, and there's a couple of ways to go about that. It's not too hard, but just accept it to be true. All right, so what I do next is I switch the order of my limits. So I'm going to take the derivative before I do the integration. Now, remember, a derivative is always a limit, an integral is always a limit. Whether that's the integral is a limit with respect to Riemann sums or with respect to Lebesgue measure or something like that, it's always, always, always a limit. Let's take it to the limit one more time. Okay, so when I get to here, I'm going to take the derivative with respect to t, right? I'm taking the derivative with respect to t. Well, that means that y is a constant for this purpose. Well, when I do that, using basic calc 1, I get y out front. Boom, I've got that. All right, so I know that the derivative of the moment generating function with respect to t is, well, that's almost the expected value of y, right? It's almost, it's got this e business in the way. I've got an e t times y in there. Well, what could I do to get rid of the e? I could plug in 0, right? All right, well, let's do that. Plug in 0, and t is a constant. So when I do that, well, the e just becomes 1, which makes it disappear, and I get the expected value of y. All right, well, when I got to here, when I got the derivative equal to this, could I have gone ahead and taken a second derivative with respect to t? Could I have taken a third derivative, fourth derivative, fifth, and so, you know, yeah. There is nothing to stop me. I could just keep on doing this, keep on knocking it out. If I repeat this, I can see that the nth derivative is going to give me the integral of y to the n times e to the t times y f of y dy. Okay, well, if I go in and I plug in 0 for t, then what's going to end up happening is that the e part disappears, and I see that I've got n to the y times the density inside the integral. Well, that's better known as the expected value of y to the n. Boom. And so here, if I take the derivative, plug in 0, this gives me a way to get the expected value of the variable to a power. And that's why it's called a moment generating function. All right, so now let's think about multivariate normal moment generating functions. All right, well, here, what I'm going to do is I want the expected value of, you know, for e to the power of t times y, but for each of the different variables in my multivariate situation. So I know that I'm going to have a bunch of e's. If I multiply a bunch of e's together, it becomes addition. Boom, we've got this up here. All right, when I look at that, I see that that is t times y, t times y, t times y all the way down. Hey, that's the multiplication of t transpose times y. So I'll go ahead and write this in a little bit cleaner manner. All right, okay. So now let's think about it. If I take the partial derivative with respect to just one of the t's, and once again, I have to be able to change the order of my limits, but that's not too hard to show if I use the dominated convergence theorem. Then what will happen is when I take the derivative on the e part, and I'm taking respect to t, you know, the y part comes down out front as using chain rule. Okay, well, I can do this again with a different t or the same one. I can keep on doing this all I want, and I can get, you know, more expected values. Well, when I plug in 0 for t, and when I say 0 this time, it's going to be the 0 vector, then this e business disappears. And boom, I can get an expected value. And that looks like something that's going to be really important for covariance, right? Maybe, Just maybe. Okay, so here's a theorem. If y is distributed normal with mu vector and sigma as the covariance, then the moment generating function is going to be t transpose times the mu vector plus t transpose sigma t multiplication all divided by 2. And I'm going to go ahead and skip this part because this is really, I'm going to assign this as a homework problem. But this is how you solve that. All right, now corollary. The moment generating function of y minus mu is just going to be this exponential. Now, why is that? Well, I know the expected value of y minus mu is going to be the 0 vector, so I get rid of the other junk in there. Easy peasy, lemon squeezy. Now, properties of moment generating functions. If two random variables have the same moment generating functions, then they have the same density. Not surprising. The second property, two random variables are independent if and only if they're a vector moment generating function factors. Okay, now, something about this is that the moment generating function has to be defined, and not every density has a moment generating function. For example, the Cauchy distribution does not. It doesn't even have an expected value. So if you ever have a density that is missing an expected value for the variable to an integer power, you know it does not have a moment generating function, because if a density has a moment generating function, then all infinitely many natural number powers of the variable have an expected value. All right, well, that's all I've got for you. Take care and goodbye.